Good morning, dear students. We were discussing about nuclear magnetic resonance spectroscopy. From various videos, uh, you must have understood what is NMR spectroscopy, what is proton NMR spectrum, what is C13 NMR spectrum, all those. And we have worked out few of the examples too. Today, I am going to discuss about a technique in NMR spectrum. That is what we call chemical exchange, or it could be even called proton exchange. So, what is a chemical exchange? So, chemical exchange means it is the exchange of a proton in between two different states. Here in the picture you could see a molecule or it could be called a state A where a proton is attached, and there is another molecule which is in a state B, or it is a different molecule where a proton is attached to that. And what is going to happen is there is a dynamic exchange between the state A and state B, or it could be called there is a dynamic equilibrium existing between the proton with the state A and the proton with the state B. And this process is called forward exchange, and this process is called backward exchange. So, chemical exchange is the exchange of proton between different molecule or between different state. And here the exchange is expressed in hertz, or it could be told in per second. And what is this chemical exchange all about? What do we discuss when we discuss about the chemical exchange? It is the rate of exchange. We are focusing on the rate of exchange. So, whether the rate is slow or the rate is intermediate or the rate is fast, that's what we are going to discuss when we discuss about the chemical exchange. Let us see what are the examples of this chemical exchange. The very first one, it is ligand protein interactions. So here in this case, state A could be considered as a free ligand and the state B could be considered as a ligand bound to the protein. For example, you can take a proton which is in free state, and in the second case it is bound to a proton. Or it could be slow conformational change in a molecule. So we have already known about the structure of the protein. The structure of protein, for example, it could be helix shape. So in helix shape, there is a proton attached in a particular conformation, and there will be a conformational change. So the proton will be in a different state. So this could be compared. And keto-enol tautomerism. We know about the keto-enol tautomerism. That is the rapid exchange between two different form of a molecule, that could be keto form or enol form. And the keto-enol form could be studied by using NMR spectroscopy, or it could be the hydrogen exchange between the solvent and the molecule. So in the state A, proton is the part of the molecule. In the state V, the proton will be transferred to the solvent. This can happen. And all this exchange could be characterized by NMR spectroscopy. The NMR spectroscopy can characterize when the proton is in a molecular state A, and the NMR spectroscopy could be characterized when the proton is the part of the state B or the part of the molecule B. So, we have a lot to study about all these examples by using NMR spectroscopy. So we would understand what are the certain aspects of this chemical exchange. We will just look into that. That is what important for us. So the first case, it could be slow. Let us take a slow exchange. For example, if we take slow exchange, when you are talking about the slow, fast, or intermediate whatsoever, it's a comparative term. So when you say slow, the exchange has to be compared with something else. When it is compared, then only you can say slow, intermediate, or fast. And we are comparing with what? The condition is this. If you wanted to say the exchange is slow, for example, if you take the K exchange from A to B, or K of exchange B to A, if it is smaller than, far smaller than the magnitude of the chemical shift A and the chemical shift B, then we can say that the chemical exchange is very slow. And you need to remember that the chemical shift is expressed in ppm, and the ppm you need to convert to hertz, because the chemical exchange is expressed in hertz. So how can you convert the ppm into hertz? So what you need to do, you have to multiply with spectrometer frequency. When you multiply with the spectrometer frequency, you get it in time scale per second. How many? So if you wanted to speak about the chemical exchange is slow or intermediate or fast, what you need to do, you need to compare the exchange rate. It's written over here. When the k value of means the exchange rate constant A to B, or the exchange rate constant B to A is far smaller than the difference in chemical shift of both the molecule or both the state, then you can say the exchange rate is very slow. Remember that the chemical shift in ppm has to be converted into time scale. That could be done by multiplying with the spectrometer frequency and converting into hertz. So I repeat, when the rate from the molecular state A to molecular state B is slow, only when the exchange rate is far smaller than the difference in the chemical shift of the molecular state A and the molecular state B. Remember that it is slow on the chemical shift time scale. Chemical shift time scale. For example, if you take this proton, which is the part of the state A or the part of the molecule, it is given as 5.1 ppm. And the chemical shift value of the molecular state B could be 6.1 ppm. So if you take the difference, just like it is shown over here, it will be 1 ppm. So suppose if you imagine the spectrometer frequency is 500 megahertz, then into 1 ppm, it could be 500 megahertz. That is the chemical shift difference, because when you use the spectrometer frequency 500 megahertz, then the 500 megahertz will be the chemical shift difference. And suppose you take the exchange rate is given, K exchange rate is almost 5 per second. That means in a second 5 times the hydrogen is getting exchanged. It is in dynamic equilibrium between the molecular state A and molecular state B 5 times. So 5 times per second. So the 5 times per second, if you compare with the 500 megahertz, that is for sure the the K exchange, the exchange rate constant A to B or exchange rate constant B to A is far smaller than the chemical shift difference 500 and 5 ppm. Suppose in another case, if the exchange rate for if you take the chemical shift difference, it could be 6 ppm here and it could be 6.1 ppm over here. If that is the case, then 0.1 ppm will be the difference. Then if you convert it into megahertz, it will be 50 megahertz. And suppose the exchange rate is somewhere instead of 5, it is 50 per second. Then these two are almost equal. When these two are almost equal, then it will come like this. When it come almost equal, it will be intermediate. It will be intermediate, please understand. And if the case is like this, that is the exchange rate is greater than the chemical shift difference, then it will be fast exchange. Please understand. Then it will be fast exchange. And I missed to write about slow exchange. Slow exchange. If it is slow exchange, what will happen is this exchange rate is far smaller than the chemical shift, and the peak will be like this. There will be two peaks. There will be two peaks. There will be two different peaks. By looking at the peak itself, you can say whether the exchange rate is slow, fast, or something like that. See here, for the intermediate state, the exchange rate is more or less equal. Then what will happen? Instead of getting two different peaks, you will get a broad peak. If it is fast exchange, what is going to happen is you will get a single peak. If you take slow exchange, you are supposed to get a peak over here and you are supposed to get a peak over here, two different peak. What will happen if it is a fast exchange? This two peak will be merged into a single one, and that merging will happen with respect to the population weighted average. Population weighted average. And the population weighted average depends on the population of the species, and PA is the population of state A and PB is the population of state B, and delta A is the chemical shift of A and delta B is the chemical shift of B, and the population generally expressed in terms of fractions. So the fraction of both must be equal to 1, just like mole fractions. 0.25 and 0.75. If you know 1.1, the other one will be 0.9 because the sum of the both has to be equal to 1. So here, if you take the case, if the population of A is 0.25 and the population of B is 0.75, then what will happen? This will be just 25. If you take the 100 meter in both the case, 25 meter away from the delta A, the merged peak will appear somewhere just after the 1/4 distance of the whole distance. If it is 0.5 and 0.5, what is going to happen? The peak will appear at the center. So it is depending on the population weighted average. Please understand that. Then how is the slow exchange could be manifested or identified? So here I am taking a particular case where the binding between the A and with B, or A could be a proton, B could be a ligand, or B could be a proton, anything. So what will happen is A and B is joining to give a complex AB, and the proton is attached to A, and in the second case proton is attached to AB. So here you can take this A is a particular reagent and B is another reagent. What we are going to do, we are going to mix strong binding. So you have taken A and mixing with B. According to the stoichiometry of the reaction, the ratio is 1 is to 1 is to 1. That is the ratio, 1 is to 1 is to 1. So if 1 mole of A combines with 1 mole of B, you will be getting 1 mole of AB complex. So here initially we have taken A and B, the ratio is 1 is to 0. So A is having a proton, that proton will show a peak. That is what given over here. In second case, what is going to do is, you are just going to add B into the solution. When you are going to add B into the solution, a part of A will definitely react with B. So a part of A, when it is definitely going to react with B, the proton will be the part of AB. So the proton is there as a part of AB. So what will happen? There will be the rising of a small peak which depends on the formation of the complex AB. So what will happen if I increase the concentration of B in the solution of A? What will happen? The half part of the A will get reacted with B, so that the ratio will become 1 is to 1. Because from 1.5 is already reacted and the other 0.5 is over here. So the ratio will be now 1 is to 1. So you are getting a two peaks which is having equal height. Suppose if you are adding again, what is going to happen if the ratio is 1 is to 1, the almost, because the stoichiometric coefficient is 1 is to 1 is to 1, almost all the part of A will get reacted in order to give B. We have already mentioned there exists a dynamic equilibrium, so there will be an equilibrium constant too. In order to maintain the equilibrium, there will be small amount of A which is unreacted. So if the slow exchange is going to happen, you could see over here the A free, that is the proton in a free state, the peak will be keep on decreasing. And what about if you take the peak of the complex, the height which represents the peak of B will be, the complex will be keep on increasing. Please understand, this is how we going to identify the exchange is slow. So this type of exchange features depends on the chemical shift of A which is in free state and the chemical shift of B which is in complex state. So chemical exchange, it is the exchange of a proton from a molecular state A to B. Then what will happen? We can study about this particular stage. For example, the significance, if you take, if you wanted to say that this exchange is very slow, that means if you wanted to say the exchange of the molecular state A to molecular state B is very slow, that means the proton doesn't want to convert to molecular state B. Suppose you take the last case where this is the hydrogen exchange between this molecule, solvent and the molecule. So this is the molecule. So when this is the molecule, you imagine the hydrogen is attached to this molecule by means of hydrogen bonding. When it is the part of hydrogen bonding, the removal of this proton from the molecule will become difficult. So solvent cannot access it. So when it is difficult, the exchange will become slow. So if the exchange is becoming slow, you can have a hint. What is that hint if you ask? The binding of the proton with the molecular state A, which is very strong. When it is very strong, the exchange will become slow. So if you know the chemical exchange rate, that will enlighten many information with respect to the molecular structure of the molecule or the molecular structure which is involved in the exchange of a proton. That is what the importance of the chemical exchange. So chemical exchange gives many informations about the molecule, especially when it is expressed, when it is the part of the molecule which is cited in the example. So this much you need to know about the chemical shift. Next, we need to get into a complex situation. What is that complex situation if you ask? Suppose there is a molecule which contain an OH group and an NH2 group. Suppose it's an amino acid. You need to identify the molecular structure. So you have taken NMR spectroscopy. So from this chemical shift scale, you could understand that the OH will come somewhere in between. Somewhere in between means when you compare it, it comes somewhere 5 to 0. Whereas if the same molecule contain an NH bond, it is supposed to fall between 4 to 2. It is at the same range of the OH. So you might be getting a peak like this. This peak may contain information about the OH as well as NH. Then how do you split them? So how will you get the proper information from NMR spectroscopy? This is what the situation that makes the NMR spectrum quite complex. So how proton NMR spectrum could be complex? The very first, when signal overlap, useful informations are varied. So we have already seen a alcoholic proton signal and a amine proton. When both are getting merged, you won't get the proper information. Another case is this proton exchange. So what will happen is when you are looking at the spectra of a particular molecule, the proton will be initially part of the molecular state A. Just when you are testing the nuclear magnetic resonance of a particular proton, within that solution, the solution is under observation, may happen some chemical exchange reaction, some proton exchange reaction. So that will give a broad spectrum, or that will give an additional peak. Of course, that is going to make the NMR spectrum complex. And hydrogen bonding will make complex. So what will happen when the solvent is mixed with this one? Then there is a possibility of forming hydrogen bonding. When a coupling constant is comparable with the chemical shift difference of the coupled proton. So if you recall the spectra, that is, there are two peaks. This distance is what we call chemical shift. And there may be another case. What can happen is there is splitting. So there is a splitting of a single peak. There is a doublet. We have already learned. And the doublet distance, if it is equivalent to the chemical shift, you will be in confusion. Is that due to the splitting J coupling, or is it due to chemical shift? In some cases, what can happen is the chemical shift distance, the difference in chemical shift could be exactly equal to the J coupling value. So there is a complexity. Both are merging. So the information will be varied. Not worried, buried. And the solvent effect. So solvent effects may have some influence on the NMR spectra that will dislocate. That also may invite complex situation.